So, very good morning. So, the title of my course is Microprocessors and Interfacing. So, first I will give the introduction to the microprocessor. So, what is a microprocessor? If you consider a digital computer block diagram. So, what are the different blocks in a digital computer? So, you require some input device through which you will take the data, input device such as keyboard and mouse, and this input data will be given to a ALU, arithmetic logic unit, which performs various arithmetic and logical operations. Arithmetic operations such as addition, multiplication, subtraction, and logical operations such as ANDing, ORing, inverting, complement, all these operations. Then to store the results, we require some output device. And you can store the programs in the memory. And you require some control logic to control all the operations. The combination of this ALU and control logic is called as a microprocessor. This is called a central processing unit, CPU. So, CPU can be made of the different circuits like adder, subtractor, and AND operation, OR operation and all, or otherwise you can build this CPU into single IC. That single IC is called a microprocessor. A CPU built into single IC, integrated circuit. Into single integrated circuit is called microprocessor. So, normally the microprocessor I will call as mu p, because mu is the symbol for the micro and p is processor. So, what is the generation of these microprocessors? So, the first microprocessor was the Intel's microprocessors. So, in this course I am going to discuss only Intel's microprocessors. The first microprocessor that was manufactured by the Intel is 4004 in the year 1971, and this is 4-bit microprocessor. So, what is the meaning of this 4-bit, 8-bit and 16-bit, 32-bit microprocessor? So, this basically decides the size of the ALU. This 4-bit implies the size of the ALU. That is, if you want to perform addition of two 4-bit numbers, we can perform in a single clock cycle. So, using this 4004. If you want to perform addition of two 8-bit numbers, it requires 2 clock cycles and so on. So, this is 4-bit microprocessor, was first fabricated in 1971. So, this is a 4-bit microprocessor and whose clock frequency is 1 kHz, and the number of pins in this IC are 16, and this memory capacity of this 4004 was just 1 kilobyte, means there are 10 address lines. So, the relation between this number of address lines and the memory capacity, the maximum memory that can be connected to the microprocessor. Here, because the memory is outside the microprocessor. If we take the simplified circuit diagram of the block diagram of this one, this is input device, we can call this IO in a single block, then this is microprocessor, the combination of ALU and control logic, then we will be having memory. This is also bidirectional because it is I/O. From input the data will be taken in this direction, and from microprocessor the data will be outputted in this direction. So, here this requires this 10 address lines and 1 kilobytes of the memory. The relation between the number of address lines and memory is the maximum memory capacity is given by is equal to 2 raised to the power of n, where n is the number of address lines. And the number of data lines will be decided by this 4-bit microprocessor, means the number of data lines will be 4 bits. So, this Intel 4004 was the first Intel's microprocessor, which is generated, which is fabricated in 1971. So, the Intel's the first 8-bit microprocessor is 8008. So, which is developed in 1972. This is Intel's first microprocessor, first 8-bit microprocessor. As I have told, 8-bit microprocessor means the size of ALU is 8-bit, and this 8008 can operate at frequencies of 800 kilohertz, and the memory capacity of this one is 16 kilobytes. That means we will be having address lines of 14, because 2 raised to the power of 14 is 16 kilobyte. And number of data lanes are this 8-bit represents the number of data lanes. Is 8. And this is the clock frequency, the important parameters of any microprocessor. So, how many address lines, how many data lines, what is the clock frequency. So, these are the 3 important parameters. And then this is actually, of course, this is 18 pin device. This was 18 pin IC. So, later as the technology developments, so the next 8-bit microprocessor only, which is 8080. So, this is developed in 1973. This is also another 8-bit microprocessor only. So, the difference between 8008 and 8080 is the clock frequency here is 800 megahertz, whereas here the clock frequency is 2 megahertz. Means the speed of this 8080 is more when compared with 8008, because here one clock cycle will take 1 by 2 megahertz. So, this is equal to 0.5 microseconds, whereas here one clock cycle will take 1 by 800 kilohertz, which is more than this 0.5 microseconds. And another difference is here we will be having 16 kilobytes of the memory only, whereas here this can connect to 64 kilobits of the memory. That is, the number of address lines are here 16. So, 2 raised to the power of 16 is 64 kilobytes. The number of data lines here is, because this is also 8-bit, same as that of 8008. So, the major advantage of this one is speed is more, as well as the memory capacity is more. So, next same 8085 microprocessor, which is one of the famous microprocessor 8-bit microprocessor. This is also 8-bit, 8085. Is also another 8-bit microprocessor developed in 1976. So, the major difference between 8085 and 8088 is, so here this clock frequency of 8088 is 2 megahertz, whereas 8085 is 3 megahertz. So, one clock period is approximately 330 nanoseconds, and the memory capacity is same. The remaining things are there, only the speed of this one is more. So, all these 8080, 8085, all these are 40 pin devices. So, number of address and data lines are same. number of data lines will be 8. So, the only difference is here the speed of 8085 is more when compared with 8080. Then the Intel's first 16-bit microprocessor is 8086. So, in this course, we are going to concentrate on 8086. So, this is Intel's first 16-bit microprocessor. So, this will be having the major differences between 8086 and 8085. One is the size of ALU here is 16-bit and the number of address lines in 8086 are 20. Implies the maximum memory that can be connected to the 8086 is maximum memory capacity is 2 raised to the power of 20, which is 1 megabyte. This is one difference, and the number of data lines are 16. And the clock frequency is here the speed of 8086 compared with 8085. Clock frequency, we have 3 versions. The standard 8086 operates at 5 megahertz clock, whereas the version 80861 operates at 8 megahertz clock, and the version 80862 operates at 10 megahertz clock. So, in this way 8086 is more popular than 8085, which is 8-bit microprocessor. So, in this course basically we are going to concentrate on 8086, the architecture, the addressing modes, the instructions, the programming and interfacing to the peripheral devices. So, coming back for this microprocessor operations. So, the block diagram of this microcontroller, as I have told, is microprocessor, IO and memory. This IO and memory are called peripherals. Without this memory and IO, the microprocessor cannot perform any function. That is why you have to connect memory to the microprocessor. The technical word used to connect this memory to microprocessor is called interfacing. So, how to interface the memory to the microprocessor, how to interface IO to the microprocessor. So, this also we are going to study in this course. So, coming for these microprocessor operations. So, what are the operations that can be performed by the microprocessor? So, the microprocessor operations can be broadly classified into 3 categories. So, one is microprocessor initiated operations. There are some operations which will be initiated by the microprocessor itself. Microprocessor initiated operations. I will discuss each operations in detail. Second one is the peripheral can interface, can initiate the operation, or there are some internal operations. Which does not need any communication with the peripheral devices. So, there are some internal operations which takes place inside the microprocessor, and there are some operations initiated by the peripheral, externally or peripherally initiated operations. Okay. So, these are the basic microprocessor. You take any general microprocessor. So, these are the only 3 operations performed by the microprocessors. There are some microprocessor initiated operations, there are some internal operations, there are some operations initiated by the external devices or the peripherals which are memory and I/O. So, coming for the first one, microprocessor initiated operations. Here there are basically 4 microprocessor initiated operations. One is the microprocessor can read from the memory read operation, because this memory is read write memory. So, you can read the data from the memory or you can write the data into the memory. So, the microprocessor wants to read the memory read operation. The second one is memory write operation. Microprocessor can write some data into the memory. Similarly, I/O read. The microprocessor can read some data from the I/O device. In fact, I/O means it is only input device. From input device it will read. And I/O write. The microprocessor can write some data into the I/O device, and basically writing will be into the I/O output device, reading will be from input device. So, these are the 3 basic operations that will be initiated by the microprocessor. Now, the question is, what are the hardware elements or what are the circuitry that is required by the microprocessor to perform these operations. So, in order to perform these operations, the microprocessor need to follow 3 steps. So, in order to perform any of these operations, the step by step procedure that has to be followed by the microprocessor to perform these memory initiated operations are: so, the first one is the microprocessor has to identify the memory or I/O with its address. Identify the memory or I/O with its address. This is something like, so if you want to deliver some item to a house in a street. So, initially you have to find out the house number. So, this is all similar to that one. So, it has to identify the memory or I/O with its address. So, in order to achieve this operation, microprocessor needs some address bus. Through address bus, this operation will be performed. So, we know that in case of 8086, the address bus capacity will be 20-bit address bus. So, the very first step is the microprocessor has to identify the memory or I/O with its address. So, after identifying this memory or I/O, then it has to generate a control signals, provide timing and synchronization signals. Such as whether it has to perform the read operation or write operation. So, we have 2 control signals read bar. So, 8086 is having 2 control signals. There are some other control signals, but for this particular operation there is read bar signal. If read bar is 0, implies read operation, because this is active low signal. If read bar is 1, it is not a read operation. Similarly, there are write bar is 0, implies write operation. Write bar is 1 means not a write operation. Similarly, there is one signal. So, we can perform read or write operation from either memory or I/O. So, how to distinguish between the memory and I/O? For that there is one control signal in 8086. I am discussing only 8086 signals only here. but this procedure is common to any microprocessor. So, there is M by I O bar signal, there is a signal called M by I O bar signal. If this is equal to 1, the operation refers to memory operation. If this is equal to 0, implies this I O operation. So, using these three control signals, one is read bar, write bar, M by I O bar, we can perform all the 4 operations that I have discussed in the last slide. That is memory read, memory write, IO read, IO write. Then how to perform memory read? If you want to perform memory read, so what will be this one? This should be 1 and this should be 0. Then only you can perform the memory read operation. So, for that you can generate the memory read signal. So, memory read signal is not directly available from the microprocessor, but using these signals we can generate the memory read all the 4 signals. Okay. So, how to perform memory read operation? So, this depends upon read bar or M by I O bar. M by I O bar is one control signal and read bar. You generate memory read bar, memory read bar. So, I am generating memory read also active low signal. Okay. Memory read bar is 0 means it is a memory read operation. If it is equal to 1, it is not a memory read operation. Okay. So, there are 4 combinations here 0 0. So, if M by I O bar is 0, read bar is 0. So, is this the memory read operation? If it is memory read operation, the memory read bar should be 0, otherwise memory read bar is 1. So, you see here this is M by I O bar is 0 means this is I O operation, not memory operation. So, we have to make this memory read bar as 1, so that it is not a memory read operation. Similarly, if I take 0 1, still this I O bar is 0 means this is I O operation. So, it is not a memory read operation. So, memory read bar is 1. If this is 1 0, so this is 1 means memory operation, read bar is 0 means read operation. So, we have to perform memory read operation. So, memory read bar should be 0. Similarly, 1 1, this is memory only but not read operation. So, memory read operation, memory bar will be 1. So, using these 3 signals, so what is the logic circuitry required to generate memory read bar? So, the memory read bar logic expression will be memory read bar is equal to, so this is 0. So, we can have M by I O bar is 1. So, M by I O bar plus RD bar. RD bar is 0 means you have to take RD bar. So, using this signals we can generate memory read bar. If memory read bar is say 0, memory read bar is 0, so then this will be 1. So, memory read bar is 1 plus anything is 1. Okay. So, similarly for these 2 combinations memory read bar is equal to 1, and for these 2 operations M by I O bar is 1. So, 1 bar becomes 0. If read bar is also 0, then only this MR bar is 0, otherwise MR bar is 1. So, if I substitute these all 4 combinations for only this particular combination, we can find MR bar as 0, otherwise MR bar is 1. So, this is the main logic circuitry that is required is you take M by I O bar, you invert, then read bar you directly give to the OR gate. This is M by I O bar, then read bar. These 2 are available from the microprocessor, and you can generate memory read bar, or you call MER bar. Here also you can write MER. Similarly, you can generate memory write bar. The difference is here in place of read bar you will be having write bar. So, similar type of the circuit will be there. Similarly, you can generate IO read bar, IO write bar. So, this is how So, we can perform all the 4 operations. First you are identifying the memory or IO with the address, then you are providing timing and control signals, then the third operation will be perform the data transfer. So, this will be performed by a data bus. So, in case of 8086 we have 16-bit data bus. So, in order to perform the very first operation, which is microprocessor initiated operations such as memory read, memory write, IO read, IO write. So, we need address bus, we need some control signals, we need some data bus. So, finally, after discussing about all these operations, I will draw the overall architecture of 8086. So, the second operation is internal operations. As I have told, there are 3 basic microprocessor operations. One is microprocessor will initiate the operations. Second one is there are some operations which takes place inside the microprocessor itself. Okay. So, what are the operations that takes place inside the microprocessor? What are the internal operation? One is stores the data. So, in order to store the data, so what is required? What are the hardware elements required to store the data inside the microprocessor? So, for this we require registers. So, registers are basically used to store the data. So, register is nothing but a combination of the flip flops. Each flip flop is capable of storing 1 bit of the information. So, here if you want to store 16 bit of the information, we require 16 flip flops connected together, D flip flops. Then if you want 8 bit, so 8 flip flops, so you have to connect. So, you might have studied these registers in your digital logic course. So, we require some registers. So, in 8086 what are the different types of the registers are available? So, there are 2 types of registers are available in 8086. So, one are called general purpose registers. They are basically we have AH, AL, BH, BL, CH, CL, DH, DL. This is register array. This AH, AL combination is called AX and this combination is called BX, this is called CX, this is called DX. We can store either 8 bit of the data or 16 bit of the data. So, even though 8086 is a 16 bit microprocessor, it can perform 8 bit operations also. So, in case of data is 8 bit, we can use either AH or AL. This AX is 16 bit. So, all these are 16 bit, X will be all 16 bits. In this AH is the higher order 8 bits. So, each one here is 8 bit, this 8 represents this is 8 bit. The higher order 8 bits of the AX will be stored in AH, the lower order 8 bits will be in AL. Similarly, higher order 8 bits of this BX is in BH, lower order will be in BL. The higher order 8 bits of CX is in CL, CH and lower order will be in CL. Similarly, here and here. So, this 8 represents the size of this particular register. So, for 8 bit operations, we will use AH, AL, BH, BL, CH, CL, DH, DL, whereas for 16 bit operations, we will use AX, BX, CX, DX. Here, this AX will act as an accumulator, 16 bit accumulator. Later we are going to show that in case of arithmetic logic unit. So, if want to perform any arithmetic logical operation, we require 2 operations, 2 operands, 2 datas. So, one of the operand has to be taken into the accumulator. So, we will discuss this while discussing about the arithmetic logic unit. So, this AX will act as a accumulator. So, the remaining BH, BL, DH, DL or BX, CX, DX, they can be used as general purpose registers to store any data. And there is some special purpose also there. CX will be used as a counter in some applications and DX will be used in some division operations. So, the specialized applications of this BX, CX, DX will be clear while discussing about the instruction set of 8086. So, these are called general purpose registers. There are some other registers called base and index registers. So, they are called 4 base and index registers, 2 base registers and 2 index registers. They are all 16-bit registers. So, one is called base pointer BP, stack pointer SP, source index SI, destination index DI. So, the base pointer, I mean a pointer register, these two are called pointer registers. Pointer registers, they will be used in stack applications and also some address calculation applications. And these two are index registers. They are used in some string operations. I will discuss what is meant by string operations later. They are basically used in string operation. They are used for address calculation. So, in case of any physical address calculation or stack related. So, stack pointer is again, this is same as 8085 stack pointer. So, stack pointer always address to the stack top. So, I will discuss the details in the, while discussing about this architecture as well as the addressing modes and the instructions. And there are some other registers called segment registers. These are very important registers in 8086. There are 4 segment registers, and along with this segment register, which is called code segment, data segment, stack segment, extra segment, and along with this there will be one instruction pointer. So, this instruction pointer is similar to the program counter in case of 8085. So, the total memory, as I have told, the microprocessor 8086 is having 20 address lines. So, 20-bit address bus is there, A19 to A0. This is the symbol for bus. The maximum memory that can be connected to this 8086 is 2 raised to the power of 20. So, the maximum memory capacity is 2 raised to the power of 20, which is equal to 1 megabyte. And the physical address of each memory location, 1 megabyte means if we start with 0000H, normally the memory will be addressed by using hexadecimal numbers. So, you know this hexadecimal number system. So, 0 to 9 is same as decimal, and 10 will be represented by 10 decimal is equivalent to A in hexadecimal. This D stands for decimal, this is hexadecimal, and 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So, in binary form 0 to 9 is same as this is 4 bits BCD, So, if I take the BCD numbers, 0 is nothing but 0 0 0 0 0 H. How to convert the hexadecimal number into binary number? Hexadecimal to binary conversion. If it is 0H, the binary will you have to write 4-bit binary equivalent. This is binary. 1H will be 0 0 0 1, 2H will be 0 0 1 0, so on up to 9H will be 1 0 0 1. A in hexadecimal will be 1 0 1 0 10. Similarly, F means 1 1 1 1. So, here if I take the starting address, 20 address lanes are there. So, 20 address lanes, 20 zeros, the starting will be having all address lanes will be zeros and ending will be having all ones, 20 ones. Here the address of this one is 20 zeros, the address of this one is 20 ones. So, in hexadecimal number system, this will becomes 5 zeros H, because each 0 is equivalent to 4 bits, 5 into 4 20 bits. So, the starting address of this memory is 0 0 0 0 0 H and the ending address will be FFF FFH, 5 Fs. Each F is equivalent to 4 bits. So, total 5 Fs. So, each F is 4 bits, so total 20 bits, all 20 ones. So, this is starting and ending address. This is called physical address. Physical address of this 8086 microprocessor is 20 bit. Whereas here the segment registers are all 16-bit registers. All segment registers as well as instruction pointer are 16-bit registers. Even though this address is physical address is 20-bit, so in the processing we are going to use only 16-bit addresses only. So, how to generate this physical address from the effective address? So, the calculation for this addresses is in case of code segment. This is code segment. So, the entire memory can be divided into segments. The entire 1 megabyte of the memory can be divided into segments of the maximum capacity 64 kilobytes. So, if I take a code segment with 64 kilobytes of the memory, out of this 1 megabyte, suppose if I use from here to here, this is one location, this is another location, this total capacity is 64 kilobytes. So, the starting address is here some 50,000 H. So, in case of 64 kilobytes, the ending address will be 5FFFF H. So, how to find out this? This is code segment. Of the memory. So, in general 1 kilo means in a digital terminology 1 kilobyte means 1024 by 8 bits. 1 byte is 8 bits. So, 1 kilo means it is not exactly equal to 1000, but it is 1024. So, the meaning of this one is 1 kilobyte means, so we will be having 1024 locations. This is 1, 2, so on up to. So, this will be having 1024 locations. And each location is capable of storing 8 bits of information. So, this can store 8 bit, this can store 8 bit. This is the meaning of this 1 kilobyte. So, if I convert this 1024 into hexadecimal, 1024 is decimal. If I convert this 1024 into hexadecimal, so in order to convert a decimal number into hexadecimal, you successively divide with 16 till the quotient is 0. 16, so this will be 16 15 times. So, this will be 16 if you want to divide by 1024, 1024 by 16, 16 6 jar 96, remainder is 6 4, 16 4 jar. So 1664 times this is 0 and 16 4s 0, 16 zeros 4. So you have to stop here. So you see the way to convert this decimal to hexadecimal number. So this is 1664 jar is 1024, so remainder is 0, 16 4 jar 64, remainder is 0, 16 zeros, remainder is 4. So totally this will be 400. So if I want to start with 0000H, so because this is 4000, one less than this one is called 3FF. For this 3FFFH, if I add 1, F is the 15 maximum number. So in case of decimal 9 is the maximum number. If I add 1, it becomes 10. So this F plus 1 becomes 10. This is 10. This is 104. Okay, if you start with 0, so you have to take the value which is 1 less than this 400H. So this 0000H to 03FFH is called as 1 kilobyte. If you want 2 kilobytes, the next address is this one is 0400H, and if you add 3HH 3FFF, this is 07FFH, this will be 2 kilobytes. So starting from 0000H to 07FFF which will be 2 kilo, up to here this is 1 kilo. So for this again if we add another 7FFF for the next address, you will get 4 kilobytes. So like that, if I take the 64 kilobytes, that you have to add FFFFH is equivalent to 64 kilobytes. If starting address is this, to get the ending address of 64 kilobytes, you have to add FFFFH. So this is physical address is 20 bit. Now code segment stores the first 16 bits of the starting of the code segment. If the code segment starting address is this, the contents of code segment register, this is the symbol for the contents of. This is contents of. In microprocessor terminology, this bracket represents contents of. So contents of code segment register will be 5000H. That is the starting 16 bit address of the starting of the code segment. Then to access any bit, so we will take the instruction pointer. Suppose if instruction pointer is having address of some 2345H. The physical address from where we are going to either read or write the data, this is the memory, can be obtained by using a physical address. This is called effective address. Physical address is given by CS code segments data into 10H plus contents of instruction pointer. So this will becomes 5000H into 10H means 50000H plus instruction pointer is 2345. So this will be 52345H. So somewhere here we will be having say 52345H. To access the data from here, either you have to read or write the information. So you have to take 5000H, the starting address. This is starting 16 bits of this code segment. You have to take into code segment register. Then the offset from here to here, what is the offset? What is the difference between this address and this 2345H? That you have to take into instruction pointer. So this is the way to store the physical to compute the physical address, knowing the code segment register and instruction point registers. So basically code segment register stores the programs. The purpose of the code segment register is to store the programs. In case of 8085, only 64 kilobytes of the memory is there. Within that 64 kilobytes of the memory, we will store the program as well as we will store the data. Whereas in case of 8086 we can have the separate segments. To store the memory, to store the program, we have code segment. To store the data, we have data segment as well as extra segment. So this is about the first register, which is code segment register, which holds the starting 16-bit address of the particular code segment. So the code segment size can be, it can go up to the 64 kilobytes of the memory. And the second segment register is data segment. As the name implies, this data segment is used to store the data. Again the same thing. So if I take this data segment out of this memory, if I define from here to here as data segment, we can go up to the maximum of 64 kilobytes. If the starting address is something, let us say 60000H, ending address of 64 kilobytes will be 6FFFFH. To read the data, to write the data into this data segment, this is basically used to store the data, to read or write the data. You can call, instead of store you can write, you can store the data, as after that you can either read or write the data. So to perform either read or write operation, again we have to take the data segment register holds the upper 16 bits of the starting out of that particular segment, starting of that particular segment. So 6000H. If you want to access the data from some location whose offset is say some 5250. So this address will be now 65250. The difference is called offset. That offset will be held by instruction pointer. So now if you want to compute the physical address, the same information, data segment into 10H plus contents of instruction pointer. So there are some advantages of this memory segmentation. One is we can access the 4 segments, which is total of maximum of 64 kilobytes here. So 4 into 64 kilobytes. So 256 kilobits of the data can be accessed simultaneously. That is one advantage of this segmentation. So another advantage of this one is we can use this same memory can be accessed by multiple users. So this microprocessor 8086 can operate in maximum mode configuration, which is multi-processor configuration, multi-user configuration. .8085 is only single user, only one user can program that particular 8085, whereas 8086 is we can have multi users, more than one user can access the same 8086. So this memory segmentation enables the 8085 to access by multiple users. That is another advantage of the memory segmentation. So one more advantage is using the 16-bit address of the segments, we can access the 20-bit physical address. So these are some special features of this 8086 compared with the 8085, where segmentation is not possible. So the next segment register is, this is data segment register, and we have stack segment register. So stack is basically, so the same definition as that in 8085. So stack is a temporary memory. So during this either subroutines or the interrupt operations, so some data need to be stored in temporarily in some locations, that will be stored in stack. So I will explain this stack register and stack operations in detail while discussing about the architecture. So stack segment, same, this holds the 16-bit, starting 16-bit of this stack segment register in exact similar manner. There is one more called extra segment. Extra segment basically stores the excessive data. There is a data segment which can store 64 kilobytes of the data. If the data is in excess of 64 kilobytes, that excess data can be stored in extra segment. Or as I have told in multi-user configuration, if two users want to share a common data, that common data also can be stored in extra segment. So, extra segment can be used for storing the excess data and also you can store the shared data among the multiple users. And also in extra segment will be used in this string operations. String is if you want to transfer a huge amount, a block of data from one location to another location, that is called string. Okay. So, in that case also we can use this extra segment. So, in extra segment we will use this offset will be stored by source index and destination index, SI and DI registers, as I have discussed in the earlier slide. So, there are two registers called source index and destination index. So, I will discuss this in detail while discussing about the instruction set. This is source index and destination index. So, these are used in string operations. Where a block of data has to be moved from one location to another location, or you have to process a block of data. That type of operation is called string operations. So, in these string operations SI and DI will be used along with this extra segment register. So, these are the different registers that are available in 8086. So, all these registers are required. So, we were discussing about the second microprocessor operation, which is internal data operations. So, internal data operation, the first operation stores the data. Second internal data operation is performs arithmetic and logical operations. This is the internal operation, as I have told in the very first slide. So, the ALU is a part of a microprocessor. ALU and control unit is called microprocessor. So, in ALU you can perform various arithmetic operations such as addition, subtraction, increment, decrement. We will discuss in detail those operations in the instruction set, and logical operations such as rotating the data, shifting the data. So, there are some operations like complement operation. So, all these operations will be performed. So, to perform this operation, the microprocessor needs a hardware device called ALU. So, in case of 8086, the size of ALU is 16 bit. That is why it is called 16 bit microprocessor. Means in order to perform 16 bit addition or 16 bit any 16 bit operation, this will take only one clock cycle. This is the second operation, which is performs arithmetic and logical operations. Third one is testing for the conditions. If you want to check between the two numbers which one is larger number, so in such applications we have to test some conditions. So, in order to test conditions, the microprocessor requires a register called which is flag register. So, in 8086 the flag register length is 16 bit. There is a 16 bit flag register in 8086. So, even though the length of this flag register is 16 bit, there are only 9 different flags. So, I will discuss that flags and what is the condition for each flag to be set or reset, that in the next class. Thank you.